Hello and welcome back to the Broentech learning video series. This is module 1 and today we will give a look at C code for the Vri board. In particular, this is the C code for the STM32. And then we'll start to go a little bit, we'll start to explore a little bit the libraries here and to see what we can do and how we can do it. So this code is available on GitHub. You can just go on github/Broentech VriFog device, and then there is the folder src, basically where there is the source code. And you can just download that, clone that repository, and you will get basically a Dac project where you can just open it with your editor and or with the Dac Idc software, and this is what you get. So you can see here that you have, if you're not familiar with this IDE, this is a free IDE which you can download it from the Cox website. And it includes everything. You have to do some settings in the configuration here to check you have to set the debugger, and you have to set also the tool chain and everything. But it's very easy, and you can easily see how to do it. This one in on your that there are a lot of videos, and also in the Cox website they have a lot of guides on how to set up the environment. Once I said that, we can start to see here that we have several libraries here. So for making things easier, I also included ST libraries directly in the project. So you already have the complete project which you can just download, open it, and start to modify it. So, and you can see here that you have the CMSIS libraries for the core, the M3. The ARM M3 core, and then you have the boot and startup configuration files, where these are written by the ST guys, which are specific for the L1. Also, you have here we have some other libraries, the syscall and standard libraries, basically where we redefine the printf and so on. And then here in the main folder we have all our libraries, which I just put without any folder, so which I can just include it. And these are these libraries here, these files are you don't have to use all of them. You can just use which one you think it's useful for you. For example, if you don't use ADC converter, then you can just skip those libraries and so on. But I include all of them because in most of the cases you will need to use a lot of those. So let's start to navigate a little bit. Here we have the IDC Handler, which basically declare the analog digital converter. Basically we can read the ADC1. These are the functions. We can read the ADC already, and it will return an unsigned integer. And you can even, and one of those actually is also used for the battery. We can read the voltage of the battery, and it's also return an integer. Just remember that if you use these functions, you have also to firstly, actually we'll do it automatically here in the, if we see the implementation of that function, is initialization, and then when we call read bat, yes, you will see that here we'll actually firstly we enable the sensing pin, and we wait a little bit because it has to charge the capacitor, and then basically then once that we enable the pin, we do the reading, and then we do the reading, and then we disable again the sensing pin. So here with this function here. So if you are a little bit uncertain what this means, I suggest you that you see the schematic, because on the schematic, basically before you do a reading for saving power, there is an access transistor there which must be activated just before you do the reading of the battery, and then you disable it, otherwise you will consume a lot of power. So And this basically is the library which you can use it. You can call this function for reading from ADC. So if you have a sensor already attached to pin A0 or pin A1 and so on, you have to check on the schematic which one is the correct pin for the ADC 0, and then you can just call these functions and read directly the voltage out from it. Here there are the configuration file. There are the configuration file. We define a lot of variables which they can be used for, which they are. Some of them are defined because, for example, this is the address, the starting address memory of the user, which we can easily, which we have access to write and read. Is actually the EPROM. This is the EPROM. This is the address of the memory EPROM, where we can just go there and modify it and so on. So we have other definition here. We also define some variables. And here we basically, in this configuration file, where we basically we set all the sleep time and basically the time which we wait for response of the gateways and so on. Also the RF configuration, for example, of the RF chip. You also have to read how the RF chip works before you will be able to understand this one. That is a mesh protocol. So basically we have to set a system ID. In this case we set it to 22222, and then we have a protocol. 0 means we are using actually packet, or 1 is transparent, so and so on. So, and the channel is number 2. Also there are some other definition here for being like, you know, for convenience here. For example, when we use printf functions, in this case we are printing on the USART1. So every time that we call printf, we'll basically print something on the USART1 port. Here we have you know, the length of the datagram, size, and the timeout, and so on. So for the communication, so we do some settings inside these files. Here, this file, it's very important. This is the datagram structure, and this is you will also need this one in case that you want to implement this datagram here. This is the same datagram which has been also implemented on the gateway side. So you will see that there is something which has been changed a little bit and modified. So I mean, you can use this one as a starting point. You don't have to use exactly this structure. You can modify it as far as you modify it both on the microcontroller board side and to the gateway side, because those two must be connected. So if you are using our say package for IoT package, then and you don't want to keep this structure because you think that is too complex or is it too small, you will do something more, you know, customized, and then you can modify this datagram structure here and the code, but you also have to modify the P gateway code when you unpack this structure and parse it into a JSON. And that's one you also have to do it. And then from there everything can be the same. So once that you have parsed in the gateway, once that you have the JSON in the gateway, then you can still send it as it is. You can use all the other functions. Here we have the EPROM handler. We use the EPROM for basically saving data, some data which must survive at the reset. So this is the starting address of the EPROM, and then we have it here. Some functions for initialize EPROM and write an int value, write a char value, or read an int value, or read a char value. Here we only pass the offset, so we don't need to know where is the base address of the EPROM. You can just pass 0 or 4 or 8. So remember that char is 4, it's 32 bit, one int, and yeah. So it's actually it's 32-bit one int, and it's 8-bit one char. So, and here you can see that there are some thing here is in particular when you initialize the EPROM, we write this value 0 F0 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 to check and once this value has been set, means that at least this was basically, we did this trick for understanding if it was the first time that we were booting a chip, or in that case we had to do all the settings, like we had to set the channel ID and the the network address and so on. So we didn't want to do this one every time, because also in the chip, in the RF chip, if we write and read every time, then you will basically decrease the you will decrease the life of the chips itself, because you are writing in a flash memory there, so it has a limited read and write cycles. So for avoiding this one and for increasing the survival of the life expectancy of the chip, we basically just did it on the first access. So, and then once that this one was initialized, then we basically set this flag in the memory where we knew it that okay, we already initialized it, we don't need to do it again. Yeah, here basically you see we also initialize the sleep time address and sleep time with 3 seconds between different readings and so on. And here we have basically the functions for writing the int and reading out the int and chars. For I2, we have another 2 functions here. These functions, they will basically handle the I2C bus, where you can just write an I2C function. These are a little bit more documented, so you can see it better. You can initialize first you have to initialize the struct and basically the bus here, and then you have also a function for checking the device, where it will tell you all the devices which are connected to this I2C. Remember that in this chip you have 2 I2C bus line, so you can basically you can choose which one to use it. And if you're using the Vri board, in one line there is the internal temperature sensor, and in the other line there are it's available on one external connector, so you can basically use it. You can attach multiple other sensors there. And here you will find a lot of functions for reading and writing on the sensors. Init GPIOs, here these functions, these 2 files here are used for, let's close a little bit this. These 2 libraries here are used basically only for initialize the GPIOs. We have some LED on the board, so these functions will basically initialize the LED. It will initialize the buttons, and it will initialize the RF config pin. This is also GPIOs for the RF module. In particular, if you want to change configuration on the RF board, basically the top board, you have to basically assert this pin first, and then basically the module will go in configuration mode. And once set in configuration mode, you are allowed to change register value inside that module. So, and this is basically, yeah, and this is why we are using this pin. And then we initialize some GPIOs which can be useful for our purposes, and of course you can go and implement these functions as you best wish, depending from your requirements. So yeah, and there is nothing magic here. If you are familiar with this structure, we initialize basically the structure in the different ports and so on. So yeah, we can see that so this is the initialization in port B, and yeah, pin 2 and pin 12 in this case. Yeah. So, and then there is the interrupt handler. We prepared everything already for you, so you can just go there and just fill up these functions that you want to, which interrupt do you need. You can just go there, and we already half implemented for you. Of course, we didn't write what to do in case of the interrupt happens. In some cases, for example, the timer interrupt, or yes, here in this case, this is the initialization of the timer, and then we enable it in the NVIC vector. Yeah, these are TC camera initialization. So these are all the initialization things, and you see that in case that we are using sysstick, this is an interrupt which is in general used for operative system. So, but you can use it even for other things. In this case, we are printing system tick executed, script interrupt executed, and so on. And also you can see also for the other timers where timer interrupt executed. So you can see that if you enable it, an external interrupt, for example, if you push a button and you want the circuit to respond on something, this is already implemented the function here. So you can just enable this interrupt external and just call your function from here or implement these functions. Okay, this is for the reinterrupt handler. You have let's skip the main. You can have the package handler. Okay, this is a little bit more complex here. You remember the datagram structure that we presented before? Well, this is used for actually sending that structure to over the Wi-Fi, over the UART in this case, but basically will be over the Wi-Fi module. So because the Wi-Fi module is connected over the UART, so basically when you call this send datagram, it will actually send it over the UART, and but it's connected on the module, and the module will read from the UART and will basically send it wirelessly to the router. So and here you can send int, a float, a char, or whatever, and you can even send ACK, NAC. You can check datagram, you can parse datagram, because this was also it's also already starting to be bidirectional. We start to implement the bidirectionality. Also, basically the gateway can send command to the board in order to trigger some GPIOs or to do something useful, for example, do some actions or do a reading or read these sensors or do whatever. But this one is we tested a little bit, it was working, but we didn't do a fully development of that one yet. But it's already here, so if you want to continue developing it, you're more than welcome, and actually let us know if you are bringing this project forward. We will try to work a little bit more, but yeah. So here you can see that for example, when you send the datagram in, you will send an header, and yes, and this you will see that there are like the header. We basically copy it first, and then in this for we basically send it to the UART1, is where it is the module, DRF module attached. So yeah, and the same things apply for everything, for all the other functions. We can send also a NAC and hack in case that, for example, if we receive a datagram, we can say, okay, hack, we receive it correctly or no. We can check a datagram if the datagram is correctly correctly received or not. Yeah, we can, you see here what we also start to implement the functions for a received package. In particular, you can have a conf command. When you receive a package, you can have a conf or an info or others. And in conf, for example, you can send SDX, where you set the ID of the board, or you can have a channel for changing transmission channel, or network ID, and so on. So basically we already start to implement some things for making even more autonomous. Basically the gateways, you can control you can change the network ID, or you can change the board ID remotely without hard coding it. So this, by the way, it was a pretty old code that we kept a little bit inside because we were not sure what to do, and now we decided to release it, open source it. Then there is the radiograph driver. These are the driver which basically are used for managing the RF board. In this case, we are using, as we explained in previous video, we are using the radiograph devices, And here you have we implemented all the functions for doing stuff. For example, opening the RF configuration, closing it, set the RF channel, and so on. So you have a lot of things, of functions which you can use it, and here they are implemented. So yeah, basically this is the protocol which they use, and we implemented this one for reading the configuration and setting all the registers and so on. Yeah, for example, here we enter in memory mode, and we set the address to write, we set a new channel, we close it, and so on. After that, there is the sensor handler. This is a little bit tricky, because this actually we start to implement something, but we just at the end we just give up, because there were so many different sensors out there, and we were able to make it work with a lot of different sensors, but every time we had to add a new sensor here, you know. So I mean, of course the best would be to have a library for each sensor. But since we just tested, this was just a testing environment, so we just were adding code here, our code, and then we are modifying it based on the different sensors. So I advise you that based on your sensor requirement, you implement some functions here, or these are some examples of how to read up the accelerometer. For example, we had an accelerometer. I don't remember exactly which accelerometer was it, but here this was the code for reading the registers and so on. We had the humidity sensor, and we have also among this one, yeah, these are the temperature sensors, the onboard yes, this was for the onboard temperature sensor, which is present on the board. And you can basically, yeah, we are reading out the temperature, and then we were collecting the part. We are basically, since the temperature reading is split into two registers, we have to read all of them and then put it together, shift the bit, and convert it to int, to float, and then basically return it. And that's what we are doing here. But now you can just call this function and you will get the float. In case that you have a new sensor, in case that you have a new sensor, you just you just implement a new function inside here, or you call it, or you use another library for your own sensor. And this one is really depending from the application, depending from what sensor are you using. So this function you will need to implement it anyway. Then the last two libraries here, the USART handler. In particular the C, yeah, in this case we are implementing some function here, fput C and fget C, this because and also we are implementing some timeout on the UART, and this was because we want to also to make it work with printf. So here we were basically yeah, we were implementing these functions for making the printf function on the USART interface instead of the screen, instead of the standard output. So yeah, apart from that, and then here you have the main. You can just basically, we have here and functions, yeah, you know, from the main here we basically select, we have, you know, a lot of commented out, and then we bring it back in, because it really depends what you want to do with the sensor. And we basically have an init all functions where basically we initialize all the sorts. This is the clock and the division, and then we initialize the USART1. This is the one which is attached to the shield, to the RF shield. We initialize the ADC, the two buses I2C, LED, EIO. We are not GPIO. We are not initializing the timers. We are initializing the RF pin, conf pin, and then we are checking if we already initialized this. basically this was the flag in the EEPROM. If this is different from that one, means that this is the first time that we are turning on this device. So you should configure the RF, you should do stuff. Otherwise, you just close the configuration and yeah, and so on. Yeah, and then here you have all the, here in the main you implement it as you think is better, like based on your requirements. You can read batteries, you read your device, and then once that you read your temperature, you can just send the datagram, for example, float, or and then here we have here we enter at the end, we enter in the sleep mode. And basically we wait for an interrupt, which will be in 3 seconds or something like that. You set this one in the config file. You set this time. So, but apart from that, this is more or less. You think this one has a. This was again, it was a very, we did this code. We wrote this code in the spare time, basically, and but it works. It works. You have just to tune it based on your requirements, and use it. My advice is that you use it as a framework for your further development. So you can just tune it and pick up the place, pick up the line, or pick up the file that you need, or the lines or the functions which may be useful for you for continuing developing it. I forgot to mention about few things about the libraries. So in particular the ST libraries here, which are these libraries. So you can see these are, if you read at the time that we were writing this code, these were the libraries which the ST was providing. But in the latest years, with also the new Nucleo boards from ST and so on, they switched these libraries with a new version of it. And in particular, those libraries, they tend to have basically an abstraction layer. So basically the idea is now that, because these libraries are only for the L1 version, so it would be nice if you could basically reuse this code for any ST family, and that was basically the idea towards the new libraries which ST has released. Unfortunately, they are not compatible with this one. So if you use the new library, then you probably need to adapt to do some changes on the code. You have to read the application note. ST has released several application note where to explain how to migrate the code from these libraries to the new one. So you will need to do some adjustment. For example, there are a small adjustment in the definition of the structure here. So all this stuff. But you can just go there. I advise that you go on our GitHub page, you just go there and explore, download the code, try to compile it. It should run. So once that you have the file there, you can just basically compile it. You can just build it and then flash it. So once now I don't have any board attached to the device, but you basically just click this button and it will actually build it. You will compile it, and then you can just you click this other one button here and it will flash it to your code. Also, if you are wondering how to connect the board to how to flash it, we have a previous video. We have explained what are the connections to do between your discovery board and the Vri board in order to flash the software. So this is only used to 2 pins, is the single wire debugger SWD. So basically the data and the clock there. So I think that was all, everything. I hope that this was informative, and I wanted just to present a little bit this project. There is more information on our GitHub page. You can go there and read the README file, and you can even ask questions on the comment section here on this video, and we'll be happy to help you. Yeah, so thank you for watching.